In this next section, we're going to take a look at the areas of trapezoids, rhombuses, and kites. So before we get to problem number 1, we're going to look at the formula for the area of a trapezoid. And that's going to be 1/2 times its height times the sum of the two bases. So you need to have 3 things in order to be able to find the area of a trapezoid. Its 2 bases and its height. So let's take a look at problem number 1 that is asking us to estimate what is the area of the state of Nevada. Because the state of Nevada is shaped roughly like a trapezoid. So we've got that this border here along the west side of Nevada is 205 miles long. Then over here it's 511 miles. And then up here, the northern border is 309 miles. So what this does is it basically takes a trapezoid, where we think of the bases being like this, and takes the bases and puts them here. So we've got enough information here because we've got base 1, base 2, and the height of the trapezoid. So let's go ahead and take our formula. A equals 1/2 h times b1 plus b2. And we're just going to fill in the given information. So 1/2 times the height is 309 times the sum of 205 and 511. So now we get 1/2 of 309 times 205 plus 511 is going to be 716. So now go ahead and take the calculator out, and we're going to run this through. What I'm going to do is I'm going to run this through instead of as a half, dividing by 2. So 309 times 716, and then divide that solution by 2, and we come up with 110,622. So the area of Nevada is roughly 110,622 miles squared. Now, the second part of this is going to be problem number 2. We're going to be looking for the area when we're not given all of that information. So you can see that we're given the bases for this trapezoid, but we don't have a height. So we've got to figure out what the height is with the information that we've got given to us. Notice over here you've got a 60-degree angle. That's going to be very important because we just talked in the last chapter about special right triangles. So guess what we're going to do? We're going to create a right triangle. The way that we're going to do that is to start at this vertex and draw a line straight down to the opposite base. And then that's going to be a right angle. Now, what we're going to end up with is composite figures, or we could solve using composite figures, but we can actually end up just using this formula here. So let's take a look at what we've got. We know that if this is 5, then the length of this segment right here has got to be 5 as well. So then that tells us by segment addition postulate, remember that from way back, is 2. So now we know that this 2 is across from the 30-degree angle. So that means that that 2 is equal to A. What we want to find out is what is this value right here. We don't care about the hypotenuse. All we care about is the height of this trapezoid. So the height of the trapezoid is the same as the length of the side that's across from 60. So remember that the side that is across from 60, the proportion for it is always going to be a square root of 2. So or a square root of 3, I'm sorry. So this is going to be 2 square root of 3. So that's what we're going to put in for our solution right there, 2 square root of 3 for that height. Now that we've got this height and we've got both bases, we can take this formula and we can start plugging in. So A equals 1/2 of the height, which is 2 square root of 3, times the sum of the bases, so 5 plus 7. So we get 1/2 times 2 square root of 3 times 12. Half and 2, they cancel out, so we're left with 12 square root of 3 units squared. And that's going to be your solution for that trapezoid. For problems 3 and 4, we're going to need the areas of rhombuses and kites. And it's a fairly simple formula. The area of a rhombus or a kite is going to be 1/2 times the first diagonal times the second diagonal. So if we look at this kite that we've got here, we can see that we've got all of the segments of the diagonals have been labeled with measurements. So we've got a 3 and a 3 and a 2 and a 5. So that means that our long diagonal, we'll call it diagonal 1, is 7, and our short diagonal is going to be 6. So now what we can do is just go ahead and fill in for our formula, 1/2 d1 times d2. So 1/2 of 7 times 6. So remember that in multiplication you can do any order that you want. So 1/2 of 6 is going to be 3 times 7 is 21. And so we get that the area of this particular kite is going to be 21 units squared. Now heading over to this rhombus, it's going to be a little bit more difficult because they've given us these decimals that we've got to contend with. And we don't have everything that we need in order to be able to solve for this rhombus. We do know that we can say that this segment is 2.5 here because one of the properties of a rhombus is that the diagonals bisect each other. Now the other key part of that is that we've got diagonals are also perpendicular to each other. So what we create are all of these, we create all of these right triangles and rhombuses. So we know that if we have the measurements of two sides of this triangle, we can find the third side by Pythagorean theorem. So we're going to go 2.5 squared plus x squared equals 6.5 squared. And when we do that, calculator, we're going to get 6.25 plus x squared equals 42.25. Now it's just a matter of isolating x squared, and we get x squared is equal to 36. And so we take the square root of x, or we take the square root of x squared and the square root of 36, and we get that x is equal to 6. So we know that that segment of the diagonal is 6. That means that this segment is also 6. So we know that the height is 12 and the width is going to be 5. So we can go back in and go a equals 1/2 times 12 times 5. 1/2 of 12 is 6, times 5 is 30. So this rhombus is going to be 30 units squared in terms of its area.